Okay, we're going to do another washer method problem, and this one's going to be about a vertical line. Anytime you rotate about a vertical line, everything needs to be in terms of y. Okay, so let's go ahead and read this question together. It says calculate the volume of the region bounded by the function y equals x to the negative 4. So right off the bat, you can see that y equals x to the negative 4 needs to be converted in terms of, basically, you're going to get x by itself. Okay, then we have the line x equals negative 1. That one's going to be good to go. X is already by itself, and then we have y equals 1 over 81 is going to be one of our boundaries. This region will be revolved around the line x equals 4. So again, anytime you revolve around a vertical line, you will have to get x by itself for the two graphs that you are, or relations rather, that you're using for your region. So initial step 0, we're going to get x by itself. So y equals x to the negative 4 is the same as y equals 1 over x to the 4th. Then we will pretty much cross multiply, divide by y, and then take the 4th root of both sides. That way we can get x by itself. We get x equals plus or minus y to the negative 1/4. So that's important because when we go to integrate, again, everything needs to be in terms of y. In other words, you have to get x by itself. It's like a substitution. Okay, so our next step, step 1, after our initial step, is to draw the Cartesian plane, and then the step after that is to draw our region. So first of all, we have our first relation, which I will draw in orange. Now, that is x to the negative 4, but as a relation, it's going to be x equals plus or minus y to the negative 1/4. So I'm going to write x equals y to the negative 1/4. Okay. And then our other relation is going to be, and I forgot the plus or minus. We'll figure out which one that is in just a second. It's either going to be plus or minus depending on your axis of rotation. Then we have this on the right, which is our next rightmost boundary. That's going to be x equals negative 1. Again, that one's good to go because x is already by itself. And then you should have upper and lower limits, and those should be in terms of y. And your upper limit's going to be y equals 1. And again, there's an easy way to figure out this upper limit where they cross. It's just the point where those two relations are equal to each other. If you set negative y to the negative 1/4 equal to negative 1, you will get y equals 1 where they cross. Now we will talk about why we use negative in just a second. Okay, so now you're going to sketch the region, and now you're going to draw the shapes of your washers. So I'll talk a little bit about how these washers come into play in terms of this cross section. Don't forget over here you have your axis of rotation, which is 4. You can see there's a huge gap here, and that gap will form these washers. Okay, step 4, sketch the lines of intersection of the washer and the region on the Cartesian plane. I'm going to kind of do this on this graph right here. Again, you have an inner radius, which this time I'm going to just use, I don't know, we'll use red. Your inner radius is formed by the closest function to your axis of rotation, and then you'll have an outer radius. I will use dark green, and it's going to be from your furthest away function. I'll already use green for the axis of rotation. We'll use blue. It's going to look like this. So these are our cross sections of our washers, and the washer. All you'll be left with is the difference between the blue and the red line will be this little gap right here, which will form your washer right here. Okay, so step 5 is to determine the function closest to the axis of rotation. In this case, it's x equals negative 1 is closest to x equals 4. So we're going to call that C. C, again, just stands for closest to. The one furthest away is our other function. Going to be x equals negative y to the negative 1/4. So now I want to talk about why we do use instead of doing plus or minus, we just use the minus. We're using the minus because it's to the left of x equals negative 1. If it were to the right, we would use positive y to the negative 1/4. And again, we find the intersection point by setting this this curve, orange curve, equal to the blue curve, so -1 equals negative y to the -1/4. You will get y equals 1 across. All right, now we're going to determine the little radius. The little radius, as you can see, this little red right here is going to be, in this case, your axis of rotation is to the right. It's going to be 4 minus -1. We give you that red line, which you can see is 5 units long. So that's what happens when your axis of rotation is to the right and you're doing vertical line, rotating about a vertical line. So r, little r, in this case is going to be equal to 5. Big R is going to be the same thing, and that you're taking your axis of rotation since to the right of your region, and it'd be the axis of rotation minus the function furthest away. 4 minus negative y to the -1/4. If you do 4 minus negative y to the -1/4, you get 4 plus y to the -1/4, which will be your big R. And again, in this case, we've used a darker blue, so I'm just going to square that off with a darker blue. Okay, so now let's go back to that washer that we labeled and see what that looks like in terms of our big radius and little radius. So here's our big radius right here. Then our little radius is going to be here, which again is actually just always going to be 5 because that's a solid line here. Okay, now we're going to determine the limits of integration. It said already that it was bounded on the bottom by 1/81. You can see it's a little bit above the x-axis, and we found that they crossed up here at y equals 1. And again, this is another reason why you want to graph these. So that means our limits are going to be 1/81 to 1. And now, again, these are in terms of y, and they have to be in terms of y because it's a vertical line and everything needs to be in terms of y. Step 11, set up the integral. Again, it's pi big R squared minus pi little r squared. We've done this enough already. You know, you can pull a pi out. Big R, we said already, was 4 plus y to the -1/4. We use blue for that. And then little r is a constant 5, so it's going to be placed by 5. And again, there's your limits in terms of y. Bottom is 1/81 and top is 1. Again, the reason we do that is because the range of our washers. These washers are going to go all the way up from 1/81 to 1. And if we find the area of all of these washers, which is infinitely from 1/81 to 1, essentially what we're doing is just integrating all those areas. And thus we get volume. So this is what our integral is going to look like. Now let's take a look and see what our solid looks like before we find it. Now just notice as I was looking at this before we look at the solid, this bottom line is 1/81. I had it as 0, just because it was so close to the x-axis. Anyway, you can see our range is still 1/81 to 1. So let's go ahead and take a look. If we revolve this around this line with this big gap, what is our solid going to look like? Okay, once again, I'm using an app, GeoGebra app created by Tom Brzezinski. Thank you, Tom, for making this free to use. Now I'm changing this a little bit. Everything's in terms of x here, but it's going to look the same as our solid when we rotate it. So here's what our region more or less looks like. We're rotating about a line which is way far away, so you would think this gap would cause the volume not to be as big, but keep in mind though, you're rotating about a very big axis, so it's going to generate a huge ring. So let's take a look and see what happens when we rotate that all the way around. We're going to get this very big ring, and I'm even going to fill it in so you can see even more so kind of what it looks like. It is a strange looking ring, but you can see why it's called the washer method, because again it hollows out because there's a gap between your axis of rotation and the region you're rotating, which looks like a flange. So we want to find the volume of this solid, which is exactly what we're doing. And again, the washers are just these cross sections that go all the way around to form this solid. So without further ado, we've set up the integral. Now we're going to integrate. And what we want to do is make this easy to integrate. So we have to FOIL this. This obviously just becomes 25 minus 25. But we will FOIL that, keep the pi outside, and then use the reverse power rule to take the antiderivative of each of these. Again, I'm not going to harp on all of this algebra. just use the reverse power rule for antiderivative, and then don't forget your limits and don't forget your pi. We will plug in our upper limit 1 first and then subtract when we plug in our lower limit. I always say to put your lower limit around brackets because you'll have to end up distributing this minus n. Okay, so once we do some algebra and some number crunching, including finding common denominators, you can pause this if you want, if you really want to investigate all of this. Just make sure you do it one step at a time. Your final answer for the volume of this solid is 256 pi over 81. As a decimal, that is around 9.93 cubic units. In fact, that gap did make a difference. It limited the volume of this ring to something quite small, and you can kind of see why, because it's hollowed out right there, and it just leaves a very thin band. So that's how the washer method works. Again, it's just pi big R squared minus pi little r squared, because there's a gap between your region and your axis of rotation. If you have any other questions about this example, let me know.